In this video we will talk about gravity and we will see how it relates to measurements of our planet. Before we go deeper into measurement techniques and observations, we will recap briefly a few physics laws that relate to gravity measurements. In the late 17th century, Sir Isaac Newton published his Principia, in which he suggested this formula which expresses the force F between two bodies independent of their distance r and a constant g, which was later called the gravitational constant. In the following, we will use capital M for the mass of the larger one and the lowercase m for the mass of the smaller one, which we will often then refer to as test mass. Looking at the equation, we can already see that the bigger any of the two or both masses get, the stronger the force between them becomes. On the other side, we see that if the distance between two masses gets larger, the attracting force between them gets smaller reciprocally to the square of this distance. Maybe we should also recall that when we talk about gravity, masses will always be attracting each other. Newton's theory might look simple when you look at the formula, but when people noticed that it can explain planetary motions as well as why apples are falling from a tree towards the ground, it was recognized that this formula was a major breakthrough for science. However, in order to apply Newton's formula, we need a value for the gravitational constant, which actually was not determined until the end of the 18th century, when British scientist Henry Cavendish carried out a laboratory experiment that provided an accurate value. And still today, no physical theory exists that can compute g numerically. Thus, we still need to derive it from highly accurate experiments, and the best value we have for it is about 6.67 times 10 to the power of minus 11 cubic meter per kilogram second squared. Equipped with this constant, we are able to measure properties of planet Earth. How? Well, first let's rewrite Newton's law, where we assume that capital M is the mass of the Earth and lowercase m is our test mass. We know that any force can be expressed as the product of mass times acceleration, and we see that we can divide the equation by the test mass on both sides, and we get an expression for acceleration. What we have done might appear trivial, but implicitly states that all objects drop with the same acceleration, which means that if they have no initial velocity, for example, we just hold them in our hand, they drop with the same speed. Strictly speaking, this holds only for frictionless conditions, but it is a very good approximation even for solid test masses that are dropped under normal air conditions. In order to point out that we deal with gravity accelerations, we write small g instead of a, and capital M is the mass of the larger body and r is the distance from the center of the larger mass to the smaller mass. All we need to do now is to measure gravity acceleration. Gravity acceleration is only depending on where we measure and how much mass an attracting body has. This means that if we measure that acceleration on the surface of the Earth, we get an idea about the total mass that acts as a force on a falling object there. Any test mass we drop at height h0 is after t seconds at height h1. Let's introduce delta h as the difference between h0 and h1. From basic physics, we know that the distance for an accelerated object after t seconds equals 0.5 times the acceleration times t squared. This means that if we measure the time it takes for a test mass to drop from h0 to h1, we are able to obtain a value for gravity acceleration at that particular location. Using this measurement, we are able to determine the total mass. However, in order to make this work, the travel distance should be short enough so that the gravity acceleration is almost constant. Let me illustrate this a little bit. If we would drop an object from a height of 100 km above the Earth's surface, it would have a significant smaller gravity acceleration as an object being dropped at the surface of the Earth. But if we drop an object 1 meter above the surface, we can safely assume that the gravity acceleration is the same on the ground and 1 meter above. To be strict, as long as we make our measurements on our planet, we need to take a second force into account when we measure falling objects. As the Earth rotates, it causes a centrifugal force Fc, proportional to the distance to the rotation axis. Fc depends also on the angular velocity omega of the rotating object. But as we can assume that the Earth's rotation is constant, only the distance d, in other words the location where we carry out a measurement, matters. Let's consider the force due to gravity, Fg, here pointing towards the center of the Earth. The total force on a falling object is the gravity force and the centrifugal force. We can simply add these two in vector form and see how it impacts the total force. On a location close to the equator, Fc gets stronger and counteracts the gravity force. On the other hand, at the poles, where we are close to the rotation axis of the Earth, there is almost no impact from centrifugal forces. As the rotation of the Earth is very stable, we can compute the impact of centrifugal forces at any location and correct our measurements in order to get pure gravity acceleration. Thank you for watching the basics of gravity measurements. We will build upon those in the next lecture.